All right, so you just observed electric charge when we were messing with the sticky tape, and they exerted electric forces. And the reason that happens is because the universe is filled with a number of fields, one of them being an electric field. We paid attention to gravitational fields last semester, and so here we go. History, the Greeks. Notice that amber, not a girl named Amber, but stuff named amber, okay? In fact, the Greek word for amber is electron, hence where we get our word electron. And when they noticed that, basically, they noticed static clean, because they had clothes back then too, okay? Benjamin Franklin, you heard of him? He was sort of a party animal, even though he was a founding father of the United States. Really smart guy. He was a scientist. You've heard or seen the pictures or whatever, the whole kite, you know, with a key and lightning, and he's lucky to be alive on many counts, including that one. All right, and so he came up with these terms that we take for granted, batteries. They had chemical batteries back then. As you saw in the movie the other day, even before Franklin, with Lavoisier and all them folks. And so positive, negative. Now, he actually got it backwards, but he knew what you knew today after the sticky tape lab, that there were two kinds of charges. Okay? And it seems that with these two charges, we get two kinds of directions of force. We get attractive and repulsive. Now, everybody knew before you came to college, generally speaking, I've not run into a student who hadn't heard, well, like charges repel and unlike charges attract. It seems like people pick that up along the way, and that's good that people know about science. You may not be as familiar with Robert Millikan, but he unfortunately was killed in World War I, but he managed to come up with a pretty ingenious apparatus. I have a separate lecture that will talk about that, among other things. But basically, he figured out what the fundamental unit of charge was by doing what it says, levitating oil droplets. And we can actually kind of fake part of that puzzle with sticky tape, but I'll show that at a later time. So it's just a little background history, etc. So I want to cause you to recall stuff that we did last semester and apply it to this semester. And so F with the superscript E, that means electric force. And there was an electric force of, say, tape 1 on tape 2. And there was an opposite one, 2 on 1. Okay? But notice the proportionalities. The force, the electric force of object 1 on object 2, I've written directly proportional to the charge on object 1 and charge 2 for the other one. Now, why is the letter Q the letter of choice for charge? I don't know. I just work here, okay? C was already used for a lot of things, so we couldn't go with that. So Q is special, and I think they just wanted it to feel special, so they did that. But Q, little q and big Q, there's what you're going to see in textbooks and whatnot for charge. It's an annoying letter to write. I wish there was something else, but it is what it is. So there's these direct proportionalities. I think during the sticky tape lab, it had you like kind of wipe charge off, and you might have noticed that there was less repulsion or attraction when you discharge some of that charge. I can't remember everything you did in the lab, but if you were to touch something that's charged, some of that charge will go onto you, and now the force of repulsion or attraction will be less because there's less charge. All right? So the basic idea is that electric force and charge are directly proportional to one another. And since forces always come in pairs, these are kind of opposites of one another. 1 on 2 and 2 on 1 are going to be equal and opposite. Newton's third law. All right? So there's this proportionality in the electric force. Now, we also should have noticed that as the distance increased, the force decreased. This is an inverse proportionality. So more charge means more force, but more distance means less force, and less distance means more force. So you should have noticed when they were far apart, no attraction or repulsion, but as you brought them closer together, it increased. So we call that an inverse proportionality. So we did a bunch of this last semester, and you've seen these sorts. It's called variation in an algebra class. You have a unit on that. Pretty basic stuff. The other thing, too, to recall is that we have two distances that happen to have the same magnitude, but the forces are directed differently along those distances. Therefore, we need to track with R1, if you will, R not necessarily meaning radius, just meaning a length. All right, so directly proportional to charge, inversely proportional to distance, and so that would be a way to state this law of the electric force. If we wanted to write a law of electric force, we would say, well, electric force directly proportional to charge, inversely proportional to distance of separation. Because charges only exert forces on other charges. It's not like a charge exerts a force on itself. That's one key idea. All right. So the dependence relation. So what I have done here, you might recall these fancy forms of 1. And force is always dependent on these other things. Force depends on charge. Force depends on distance, and in particular ways. So if I bring in all of these fancy forms of 1, all I've done is preserve the identity on force, because I know that the force equals itself, and I know that the reciprocal forces equal each other. So all I've done is bring in the interaction variables in a way that's mathematically sound. All I've done is preserve the identity here. So we did a bunch of this last semester, and we're going to remind ourselves a few times this semester, but we're not going to build every law from scratch. But we are going to start off this way, and then we'll do less of this as we move forward. But those dependence relations, I really haven't segregated them in a way that gets me to a law. So interaction. The interaction is here, where I have force is directly related to charge, both of them, and force is inversely related to separation distance. That's what R is. It's the distance between the charged objects, or the charges themselves. That's what we mean by that distance R1 or R2, which are always going to be the same length because it's between two charges. One length, two different directions. So separating the variables like this puts the dependence relations more explicitly. So the dependence is now kind of bottled up in here. I'm gonna switch to so those would be essentially the dependence relations, which leaves us with what we've noticed before, is that the leftovers here end up being our constant of proportionality, our conversion factor. Basically, this yellow glob of stuff converts the red and blue glob into force. So this right here, that's K. These are the same thing. Our conversion factor is that leftover part. So we're just kind of taking a detour here. So there's a value that could be computed, and there is a standard value for K that we're going to expose here in a minute, and a way to think about that. But basically, the force value, R squared per Q squared, if you will, is that conversion factor. So one way that we could think about this is if we were to separate two tapes that are attractive, and let's say we just let one hang. We had like two books we could tape it to, and just kind of let it hang. Then we brought the other one near. Eventually it would lift it up and they would kind of be suspended in space there. So we would know that the electric force at some distance would be equal to whatever the weight of that piece of tape was. And we could basically work our way to this conversion factor if we knew what the charge values were. So there's some things we just have to end up assuming because we don't have the fancy toys to go do Millikan's oil drop and all that jazz. So now vectors. Been a while since we played with vectors, so we're going to start playing with them again. It is the case that the magnitude of the length from 1 to 2 equals the magnitude of the length from 2 to 1. That means I can call them just 1, the magnitude of R, and we can kind of just, that we would write it that way. These two things here are saying the same thing. I could just write R, or I could write the magnitude of the vector R. That's the symbolic lingo. So just it's a point of clarification here. Not like you're going to have a test question. Write this out. It's just, there's a lot of lingo. And so I want to, in these lectures, which there'll be a lot more of this semester, I just want to try to make sure that we dwell on those points because they can get confusing if you forget the symbolic norms. All right. So we get this inverse square law out of all this. Why is it inverse square? Because the square is in the bottom. So 1 over R squared, inverse square. It's necessarily an inverse square because of the interaction up here. And because I actually have two vectors. I have an R1 vector going one way and an R2 vector going the opposite way. They have the same magnitude. It's not inverse square because it's the best fit, because I can show you on Wednesday, I think, I can get a better mathematical fit. It just violates physical reality. I can get a curve that fits with a higher coefficient of determination, or R squared, but it does things that are not physical, whereas the regular inverse square does. But anyways, so this law, the electric force of 1 on 2, is going to be this constant K that we derived, if you will, times the product of charges over the distance between them squared. This is a magnitude. If it were a vector, I'd have to have a unit vector, and we'll show that later. So I'm just trying to keep it as basic as it can be in terms of our lawmaking scheme from last semester. Hopefully there's some familiarity there. And it would be the case that the negative of this right here would be the other way. So, but their magnitudes are identical, directions. That negative would give us a direction, basically indicating a vector. So just, that's the basics, right? The basics of it. So yes, it works. All right. This is the full-on vector definition of Coulomb's law. We were just looking at it in its easier magnitude-only form. But let me point out this right here, this is the magnitude part. This right here is the direction part, or unit vector. We worked that out last semester too. This F with an arrow on it, that's a force vector. We've done that plenty of times. Okay, so this is our first lecture of the E&M semester. Forces are still forces. They come in different types because the field that is responsible for that force existing are different fields. We had gravitational fields last semester. We had other forces. We had a frictional force, which we're going to find out, and I sort of alluded to it, is actually a result of electricity. In fact, the structure of matter is because of electricity. Hopefully you picked that up in chemistry. All right? So this is a vector law, and vectors have magnitude and direction. So some of our calculations are going to involve, in fact, this lecture is a very vector-oriented lecture. I have a follow-up lecture that reviews it and takes it in a slightly different direction. So you're going to get repeated offenses here, visual and intellectual offense to your brain, all right? So you'll get plenty of going over it, and then these go to YouTube so you can watch it later if you need to. All right? So that's just the formal definition of Coulomb's law. Coulomb was some dude who worked this out. And it is the case that this constant has a value 9 times 10 to the 9th, 9 billion Newton meter squared per Coulomb squared. This is just a multiplier. And you might recall that the big G for Newton's law of gravity was a 10 to the minus 11. Gravity is a very weak force. Electricity is an insanely strong force. The strong nuclear force is bigger, but electricity is a big deal, especially if you've ever felt it. So, do want to point out that Coulomb's law has that same structure as Newton's law of gravity in that inverse square business. So these Newton's law of gravity and Coulomb's law for electricity are kind of a big deal. And interesting that two of the main forces in the universe have this structure. They do. All right, so that's the basic definition. So let's do an example. Given two 1 Coulomb charges that are separated by a distance of 1 meter, what's the magnitude of electric force between them? Well, if I just plug in Chugville here, so two 1 Coulomb charges. There's one, there's another one. Separated by a distance of 1 meter. makes it into the formula. The constant that we just pulled out of the box there. This is a really nice problem because it's a bunch of ones. But we get a pretty large 9 billion newtons. Which is roughly 1 million tons. This would be like a space shuttle on top of you or something, okay? Thankfully, you don't find 1 coulomb charges around very often because that is an insane amount of charge. Realize that the fundamental unit of charge, does anybody remember the value? Or the power of 10 multiplier that goes with it? Should have seen it in chemistry. It's 1.6 times 10 to the minus 19 coulombs. So 1 electron has a charge. Protons, electrons have the same charge, just different signs. The elementary unit of charge, which we'll get to in a minute, 10 to the minus 19. So 1 coulomb, that's a lot of electrons. And if you were anywhere near this, it would be bad for you, okay, to experience this much force due to 2 1 coulomb charges only separated by the distance of a meter stick. So just given, this example is literally to just give you a feel for the magnitude of electric force and what it would mean to have 1 coulomb of charge interact with another coulomb of charge. We typically have all of our problems, and because this is the way reality is with the stuff that we use, we're talking about microcoulombs and nanocoulombs. Millionth of a coulomb, billionth of a coulomb. That's typically the way this works. All right. Then I could follow up and say, okay, what is the acceleration of either object carrying that much charge if the mass of each charged object is just 1 kilogram? So we have a force of this much acting on 1 kilogram. What would be the acceleration? So this is Newton's second law, F equals ma. The net force in this case would just be the electric force. We didn't mention any other forces. Remember, net force, that's ma. We spent a big chunk of first semester. You add up all the forces, that equals ma. There was only one force in town this time, so ma ends up being this 9 times 10 to the minus 9th, like we found up here. So we solve for a. So 9 billion meters per second squared. We could also write it as newtons per kilogram. So just think of it. If somebody was, say, 100 kilograms, that would divide nicely. So would 90. You're still talking about, 10 million newtons. That's crazy. Or 100 million newtons, rather. That's a lot. That's a lot of acceleration. So there's the newtons per kilogram way of thinking about it is thinking about it the way you would feel it if it were, say, a weight on top of you. But this meters per second squared, that's an acceleration. This is going to produce a change in velocity. That's a humongous change in that magnitude of acceleration. Well, that would kill a person. All right. But charges are pretty durable. All right. But that's the point here is, dang, that's a lot of acceleration. So as we study electricity, which is probably almost half of the course, okay, the thing that this and other examples will bring to you is, okay, wow, electric forces are quite potent, and that explains a lot of the behavior that I can see or try to perceive. So for example, those of you doing pharmacy, your chem and your OChem and stuff you do later, when you understand that drugs are electric interactions. And drugs get a lot of things done. So this tiny little bit of substance has a humongous effect in our nervous systems, and et cetera, et cetera. All right. Assuming that it were physically possible, how long will it take that charged object to get to the speed of light? So let me be clear. It is not physically possible to accelerate an object that has mass, which is all objects have mass, to the speed of light. But just to make the case of how big that acceleration is, we could do some old kinematics here. So given that speed, so if it starts at 0, okay, and its final velocity becomes c, then I can use the second zeroth law. That's what this was, or actually this. That was the second zeroth law. Final speed is initial speed plus acceleration times time. If we assume it starts at rest, we just calculated this acceleration from the force interaction. We can solve that equation for time, which I show here. And so if it were possible to do this, which it is not, we would obtain the speed of light in 3/100ths of a second. That object, this 1 kilogram object with a coulomb of charge on it, we'd get to the speed of light in 0.03 seconds. So even if it were possible, it would kill any human. That's not enough time. You need a lot longer time to distribute the impulse for critters. Critters die when you do this. Okay. and any object with structure would be smashed flatter than a piece of paper in that regard. So makes for some nice science fiction. But again, remember, this demo here is simply apply basically Newtonian level kinds of physics to this just to see the import of how big the electric force is, how powerful it is. All right. The Large Hadron Collider. Anybody heard of it?
This class.
I had a brief moment of fear when I brought this slide up, because the first time I lectured on this a while back, the first time I made the slide, the two middle letters of hadron were transposed, and that produced quite an entertaining moment in the lecture that was irrecoverable.
Just kidding.
So that slide was fixed, but I can't ditch the memory of that faux pas. All right. But over in Switzerland, there is this 100 meters beneath ground, the 17-kilometer, it's either its diameter or its length, I can't remember, tunnel, circular tunnel. And we will shoot a proton, two protons in opposite directions. It's huge magnetic bottles, if you will, that keep it on its path. And every so often there's a electric field generator. And basically what I mean by electric field generator, if you could just picture, you're taking your kid, brother or sister to the park and you're pushing a merry-go-round. And every time that pole comes around, you give it another push. Okay, so these electric field generators, because charges interact with electric fields, they don't interact with anything else. So you're giving a nudge, getting it up to speed. And when we decide that the speed that we're looking for in this collision is right because you add speeds, then somebody flips a switch and one of the series of magnetic containment things puts them on an intersection course. So they run into each other, our detector picks up that interaction, we get a high energy, double the energy of one particle since they're hitting each other, and we learn stuff. So you might have heard of the Higgs boson. We discovered, quote-unquote, God particle. A lot of people were calling it. Higgs didn't call it that, but that's a historical thing that has come into it. Basically defines how we have mass in the universe. The Higgs field is what gives particles mass. Right? And so we were able to create that high level of energy and go, oh, that worked. And so the funny thing about it, or the amazing thing about it, is Higgs was a theoretical physicist. He just predicted this on paper like 60 years ago, in the 50s. He didn't have, and like at the time, like, well, wonder if we'll ever get to do the experiment on this. That's one of the reasons why we do these accelerator things, right?
Aren't they the boss of making a bigger one right now?
I think so. I think China is. So anyways, this thing gets things up to just 3 meters per second, shy of the speed of light. Takes an insane amount of energy. Tera electron volts.
How
So
much does it cost to run something?
it costs a lot. There's a multi-billion dollar apparatus that took over a decade to build, multinational,
Like,
etc.
outside of like the time and the resources and the money that it took to build it, how much does it cost to run it?
It costs not as much, but there's a lot of power generated there. Okay.
I'm surprised we haven't gone like, I don't know, power outage or anything like that. Just 'cause
No, they're
it'd be a completely closed system. Like, it would.
all right. So, just a little current events there, I guess. The electric field. So, you got to experience firsthand charges due to sticky tapes, same charges that you're used to with static cling. All right, so everyday part of life. They exerted a force because forces are those things that cause a change in speed, generally speaking. And so, as I said previously, charged particles don't exert forces on themselves, but rather they experience a force generated by something else, namely another charged particle. So the idea, and as you saw in the movie with Faraday, Faraday essentially is the guy that introduced field theory, but he certainly did in that interaction. He's, what is it? How would these forces, when there's no contact, generate the effect that we expect with forces? That we, at that time, if you remember, everything was a contact force. There wasn't these other things, well, except for gravity. So, the definition of the electric field has the exact structure of every field force, in that it's always force per unit, whatever quantity interacts in that field. So last semester I showed you that the gravitational field force was force per unit mass. So for gravity, we would have had the gravitational force, little g was our field strength, and that was gravitational force per unit mass. And little g was technically a particular constant value of acceleration, so you'd have Newton's second law in that. So, but this was field strength. Little g is field strength, and fields always have a force per unit whatever interacts in that field. Mass interacts in a gravity field. Charge interacts in an electric field. When we get to magnetic fields, it's force per unit moving charge, so it's Q times V for speed. More on that later. But we have this field idea here. And so I'm going to pause this here. One of the important things, and I think it shows up in some of the quiz questions, is about how these fields work. Charge cannot exert a force on itself. Okay? A charge generates an electric field that affects other charges. So, what I'm trying to point out with these subscripts is the electric field due to charge 1, okay, or the electric field at location 1 is the force on charge 2 per unit charge 2. This is a subtle idea. And which way to look at it makes more sense is going to be up to you. But the force on charge 2, that's what I'm saying here, is due to the magnitude of charge 2 and the electric field that's due to some other charge, namely charge 1. Okay, so just like in that simulation, I paused the video to look at, it was those sensors are charges, and they experience a force due to some other charge. So here's the electric field equation. So first thing I want to point out is this right here, this is just Coulomb's law. That was like one of the things we started off with. That is that KQQ per R squared, that is the full expression of the electric force. The electric field is defined as that force per unit charge. And so this charge 2 and that charge 2 are going to drop out, and you end up getting what we were pointing to a minute ago. Electric field, mathematically, the magnitude of the field is that green bubble right there. The electric field of charge 1 is basically the relationship that exists between that amount of charge and then some distance. So E sub 1 is the field at some distance. And then just hopefully you remember unit vectors is R per R. So this right here, I wouldn't worry so hard about taking down a copious amount of notes about it. It is true, but you're not going to need to be able to necessarily recall that part from memory. This would be the thing that all the math does is let me say that. Electric fields directed along a straight line from one charge to another. And the sign of the charge will determine the final direction of the force applied by the source charge. And we saw that in that simulation thing. You know, plus charges went away, minus charges went towards. And that's because that test charge is a positive test charge. That's an assumption that's not, every textbook says it, okay? But it's easy to forget, all right? Easy to forget. All right, another problem. This one getting a little bit more specific and not so plain Jane. So an alpha particle, or a helium, has a 2e charge on it, so that means, in case you missed earlier, E, the fundamental unit of charge, is defined to be that many coulombs. So one of the things that we'll need to know is that E, is 1.6 times 10 to the minus 19 coulombs. That's the fundamental charge. Protons and electrons have that fundamental charge. Protons are +1, electrons are -1 of those. Then we're told the alpha particle experiences a force of basically that in the y direction. Okay, so this is, remember, x, y, z, it's just a vector notation. We did that in Python when we were telling forces to go places, speeds and whatnot, so it's just a 3D vector. So really I'm dealing with a magnitude here. I have a single direction on this force minus y direction. So what's the electric field at that location? So this is an example cooked up simply so we could use that formula that we just went blurry-eyed on a minute ago. Okay? That's all we're doing here. So we card out this equation. Electric field is force per unit charge. The force that we got from the problem statement. Charge, we should be able to figure out from what we know about chemistry and whatnot. And so we just divide. And the x and the y parts are going to stay 0 because 0 divided by anything is still 0. But this number divided by that product is going to bust out to 300, or minus 300. And the electric field is newtons per coulomb. Now, in the simulation that we're going to run on Wednesday's lab, it shows the electric field is volts per meter. Same thing. We haven't defined the volt yet, but we will. All right. So negative 300 newtons per coulomb. Think of it. A newton's a quarter pound, so do the math. How many pounds force is 300 newtons? All right. Well, I think my weight is roughly, I wish I was 900 newtons. I think I'm closer to 1,000. But anyways, a third of my weight, roughly. Really, well, that's a gross estimate, okay? So that's a lot of pounds to put on one helium particle. All right? It's a super duper tiny small thing. That's a heck of a lot of force on something's mass. The mass of this particle is insanely small. Right? If the alpha particle were to be replaced by an electron, what's the force in the electrons? It's just really using the, hopefully you see that E equals F per Q is the same as F equals charge times E. That is the Q, if you will. In this case, if I replace it, alpha particle replaced by an electron. So I take this force that we just dealt with, or electric field rather, that comes down here. The electron charge comes into that, and we come up with this. That's a pretty small amount of force. 10 to the minus 17 is essentially, well, 10 to the minus 12 is a trillionth. So this is heading towards a millionth of a trillionth. If it was 10 to the minus 18, it'd be a millionth of a trillionth of a Newton. But we're talking about an electron whose mass is 10 to the minus 31 kilograms. So it's a lot of force even for a single electron. So I want to ask this question again. So if my electron obtains this force, which is seemingly small, what acceleration will it obtain as a result of undergoing that force? Good question. I'm glad you asked. Good old F equals ma again. So mass of an electron, you could look that up. 9 times 10 to the minus 31 kilograms. It's not very big. The force is what we obtained up here as a result of working on the electric field. And so if I divide the force by the mass, I get this insane 53 trillion meters per second squared. Oh my, 53 trillion meters per second every second. So just remember, meters per second is a meters per second per second. Meters per second squared is that. So that means every second under this force, if it were physically possible, this electron would obtain a speed greater than the speed of light. Because the speed of light is 3 times 10 to the 8th meters per second. And we're talking about 53.3 trillion meters per second every second. That's the change in speed that it would obtain if I could put this force on it. Which these kinds of forces are put on it, but that it doesn't produce superluminal velocities for these massive particles. But it does explain why there's so much energy, so to speak, that the universe is just bubbling with constantly, even stuff that doesn't appear to be in motion. When you break apart atoms, you're breaking up these sorts of charge collections. So, you know, how many times in chemistry was there some sort of reaction that you obtained and you're like, dang, that's a lot? Okay? This is why. Underneath the hood, this is what's happening. It's these kinds of forces producing or trying to produce these kinds of accelerations that are the reason that such a little bitty tiny speck of something, if you put it in the right conditions, will have this incredible interaction. It's because of the power of the electric field. It is insanely large. All right, so here's just something all at once. So you will get a handout of this lecture and you can watch the video. Probably more important on this slide is just to follow with me what's going on as I highlight stuff. All right? So let's just say that there's an electric field, and at some location, so this is a 3D, well, technically it's just a 2D system because I have my X and my Y. So looking down at a piece of paper, go down a little bit in the negative, or go over to the left a little bit on the negative, and up about the same amount on the positive Y. There's some location offset from the origin right there in quadrant, what is that, 2? So there's some location. The electric field at that location has an X and a Y component, non-zero. So just like in that simulation that I showed a minute ago, I could put an electric field sensor, just pretend that they exist, because they do. And I put it at that location, and I get this measurement. That there's an electric field that is 6,500 units of oomph, electric oomph, all right, in the X direction and negative 9,000, roughly, in the Y direction is the field. And so that means that if I let a charged particle loose at that location, its force would be directed in whatever the sum of those X and Y vectors would be. All right? So the magnitude of that field, the magnitude of any vector is always, hopefully you remember this, it's just Pythagorean identity. X part squared plus Y part squared, the square root of that sum. Okay, so literally, draw a picture here. There's an electric field. It had a positive X part and a negative Y part, okay, that were about this on par with one another, which means the sum of those is, something like that. Electric field, net electric field would be something like that if we were to draw the picture out. So we are able to we plug and chug and we say, oh, the magnitude, and all that's really important here is getting a feel for it. Basically 10,000, almost 11,000, because 10 to the 3 would be 1,000. Okay, so 10,000 newtons per coulomb, if you will, 10.8 thousand, 10,800. That's the size of the electric field. Where is the source? Okay, if it's the case that the only charged particle in the vicinity is a -3 nanocoulombs. -3 times 10 to the -9 coulombs. That's the only charge anywhere in town. Where is it located? Okay, well, it happens to be the case that this is the math version of any vector, except in this case it's applied to the electric field. This is equal to that. So whatever magnitude I get out of just doing the math, the Pythagorean math of that vector, that value is what this has to be by definition. So we've already developed that definition based on Coulomb's law. What's the Coulomb's force per unit charge? I get the electric field idea. Now I can use math plus physics. First line was math. Second line is I'm going to use that math value in my physics. Okay? And I could basically do math and figure out, okay, here's how far away that charge is. Okay? It doesn't tell me where yet, it just tells me how far away from this location it is. I'll do something else. So literally rearrange this equation till you get R. K is already known. Q was given. And this was obtained by the Pythagorean formula. So, you guys have been drinking from the fire hydrant called First Lecture in Electric Force. Your lips are stretched out, your cheeks have been pulled and stretched out by this flood of knowledge. So, one, this is a good example. You'll want to come back and look at this math. But when you look at it, I want you to understand what I was just saying. So I'm going to say it again, so that there can be some emphasis on all of my syllables. This is thinking about the electric field mathematically, literally, Pythagoristically. That's a word. Just taking advantage of the fact that this sets up in a nice little vector triangle business. We spent a fair amount of time in first semester doing that. All right? This is actually, I guess, physics. It's a field, it's applying a field definition. That we developed mathematically and conceptually. And then we get back to, this is math again. Just practical application. I can take that equation and do what I want with it as long as I obey rules. And so we're able to find out, oh, it's, 5 centimeters away, I guess. So just want to emphasize the way that this works out. So it's just the distance. It doesn't tell me location. So in order to find that, we've got to take advantage of something. So I want to point out, here is the definition. And I could do this with any vector quantity. The unit vector for the electric field is going to be the electric field vector itself, the full vector. That's what's up here. Divided by its magnitude, which is that. That gives me, why we call it a unit vector is stupid, because it ain't got no units. All the units went away. The newtons per coulomb divided by newtons per coulomb just gives you numbers. There end up being cosines of angles. It happens to be the case that the pointer for the separation distance is the same as the pointer for the field, or the negative of it. So I can also, this right here, this is basically a vector definition. A vector is its magnitude and its direction. The vector, its magnitude, its direction. So since though that's true, and since I have all of this data, that means that I can say, I can make an equivalence between E hat and R hat. And if I find out the magnitude of the R vector, which that's what this is, I'm in business. Or that's part of it. That's one of the locations. The other one is 0. So the next slide is going to be us simply taking what we got from this slide. The fact that the direction of the field and the direction of the position vector have to be along the same line, then I can actually figure out where this thing is located. So, continued. So, this is given all of that stuff that I just said. Where is the vector location for the source, or R1? This is going all the way back to first semester physics, which you probably have forgotten a fair amount of, which is normal. So, you have 3 seconds to write all that down. So let's zero in on this first. So I'm going to, the information that was on the last screen, E vector was this. That was given in the problem. The magnitude of E we calculated by Pythagorean's identity. That means the unit vector is just this simple x, y, z direction. The direction of the electric field, like I showed that we worked out, remember? We had this, and out here at this location, we had determined, based on those things, that the field was pointing this way. Well, doesn't this sort of match that? Okay, it's at least generally correct here. Now, this right here is true by virtue of the way we define vectors and the fact that the electric field is directed along this position vector line between the two, the source and the location that we're measuring at. So we get to make this statement, is that the direction of the electric field is the negative of the direction of the position vector. So remember, position vector is, if I have some point of origin and some final destination, what's the line directed from between those two spots? That's all we're doing here. It's a little mathematical sorcery. Well, that's how I get from the electric field stuff, which was all I was given to start with, minus one part of my location vector. I get to do this. Well, yay. I have part of my basic definition, this right here. Again, like I said before, that is the definition of the position vector. Vector equals its magnitude times its direction, which happens to be known now as this. The magnitude, you may not remember, we just found it a minute ago. It's 5 centimeters. That's how far away the source is from the location where we're measuring the electric field. That means if I multiply those two things, then I will get, you multiply those two together and voila, you get that right there. However, that's not the source location. Okay, we're looking for R1. I think I needed to. And so we get down to this here. So the point that I want to make here, step by step, all of this was basically introductory algebra. But each step was kind of busy. Okay? So you're going to want to have good notes, either that you took now, or when I give you the handout, which will look just like this, and the video, which is a recording of this, you will have that to go back on. I'm also going to do another lecture that's essentially a rehash of this with a few extra bells and whistles. So we're going to have multiple, every lecture is really a pair, sometimes a trio of lectures, because it takes, it's like a good Italian sauce. You have to stew on it for a while and add things to it and stir it for it to sink in and become great. You all at once, you know, I'm introducing you to this, and I'm not expecting that you're going to perfectly get this in one setting. This is important. A force field, the concept of a force field is that its source, whatever the source is, be it gravitational, electric, magnetic, nuclear, whatever, it's capable of altering the space around it in a way that influences objects with the capacity to interact with that field. So one of those things I was discussing, a relativistic version of gravity, is about how space is curved, and massive objects are the reason that space is curved, and that's why things take the paths that they take. You know, there's either a greater hill or valley than the last thing it interacted with. It's not necessarily a point-to-point interaction, even though that approximated fairly well. So there is some conceptual pay dirt in just realizing that fields, the way we conceive of them, is they alter the space near them in a way that produces interaction. So if you remember Faraday in the movie, he's like, well, they're invisible lines of force emanating from the wire. And there had to be something like that because it made the compass needle deflect. We'll actually do that experiment. Okay? A modern version of that experiment. And there will be no inhaling of helium like Davies, okay? None of that. Do that on your own time. All right. We will continue the abuse. So, -1 nanocoulomb charge placed at the origin, meaning at 0, 0. What is the electric strength at these 3 points? So, how would we go about doing this fun for the whole family math experiment? Yay. Again, honestly, you know, scribble all the notes you want. I think you'll get more out of just trying to follow the big picture of it, but it's your call. It's America. So, the electric field at point 1. All right. So notice here, each one of these, they're single direction. So 1 centimeter away, that's 0.01 meters. Okay. 1 centimeter away in X and Y direction is going to be that basically 1.41 centimeters. Okay, so I'm skipping some of the basic Pythagorean math here. Okay, so there's steps I've skipped just for efficiency here. Otherwise, all this other stuff, you know, K, that ain't going to change. It's just a constant. Q, still just an elementary unit of charge. So these equations, you plug and chug, they get busy real fast. which is common in the sciences, okay? And so we're able to obtain that the electric field at location 1, due to a minus 1 nanocoulomb, going to be 90,000 newtons per coulomb, which is a lot, okay? And at point 3, going to be the 40,000. So, yeah, we figured out the electric field at multiple locations. It wasn't hard. It's basic algebra, plug and Chugsville. Nothing huge short there. Now, gets a little bit more involved. This unit vector, R1, why is it 0, -1 when the location was 0, 1? Well, a little bit ago we were just talking about how the electric field direction is minus R, or vice versa. All right? So please pay attention. Your conversations other time. So that means the direction of the field is going to get that when you multiply that R hat. So remember, these are magnitudes. So when this turns into a vector, it'll be because I multiplied by the unit vector. That's why a plus 90,000 becomes a minus 90,000. So it went from magnitude to a vector. All right. E2, I didn't do E2 because hopefully you see that 0, 1 and 1, 0, just turn it around. The math isn't going to be the same, or it's going to be the same. That's why they were covered all at once in this spot here. What's going to be different is the direction. And then the same down here. The unit vector part, there's two ways we could have done it. This way is one way to always do the unit vector is going to be the cosine of whatever angle is between the axes. Or we could have taken the vector, divided by its own magnitude, and come up with a multiplier that would have generated the 31,800. Okay. More on that later. Just one last thing. You're like, yay, great, bunch of math, physics. What am I going to do with it? Why does it matter? In a very general and vague way, the math that we did here in determining field strengths and the locations that something would be, think medical imaging. Okay? Now, this is a gross oversimplification of, say, what an MRI or a CAT scan is, but generally speaking, we're talking about charged particles that are moving within electric and or magnetic fields. So the fancy gadgets that tell you how sick you are or are not, okay, it's because we have a detector that senses electric magnetic fields, and we're able to image and say, ah, the whatever that interacted in the field is at that location. And here's the strength of the field at that location. That gives us all the information that we need to do some mathematical sorcery and produce an image that says, ah, there's a tumor there, or there's not, whatever it is. All right. More on that later. We'll get deeper and more explicit and more correct, if you will, because I was doing a gross oversimplification there. But it's generally true. Oh, the idea is correct. All right. So those examples, yay. There's this superposition principle that you've already used. And it was when we were doing net force calculations, we would just add up all the forces, force 1, force 2, force 3, whatever it was, in whatever directions they were. You've already applied the superposition principle, all right? And so this thing here that I'm going to read, which every now and then pays, for all linear systems, the net response at some given place and time caused by an interaction is the sum of the influence which would have been caused by each interacting quantity individually. So like on that last slide, we did, okay, here's the electric field 1 and 2, here's the electric field 3, and if we wanted to, we could add up all those vectors and we'd have a net electric field. And we'd get that because we would obtain what each individual one at a time influence is between two interacting things. All right? So all I did here, this is sort of the, you could Google this actually, applies to anything really, but it's, and just make it a point because the superposition word will come up. This is the general physical mathematical definition. The shorter story is add up all the dang forces or add up all the dang field values and get a net result. All right, that's the simpler, more straightforward way to put it. If I were to apply it to the electric field, it's exactly what I was saying. The superposition is the net electric field or location. It's a vector sum of all the individual fields contributed by all the charged particles in net space. Now, this next part really is a dang lie, but it still works out. The electric field of an individual charge is not affected by the electric field of any other charged particle. That's true and not true. The field of a particle, yeah, it absolutely is true. If I have one charged particle over here, it's not going to change the field of another particle. However, it will change the net electric field in the space. And so if they're unequal, then there'll be a distorted sort of field picture versus a uniform field picture. All right. Wednesday's lab is going to be about those electric field maps, if you will. We'll get a clearer picture of how that works out. So it is technically true what I highlighted in red. However, the way that it works out in space, it will alter the space around those charges, and that may or may not be uniform. Probably not. So some consequences. So you think about it, matter is made up of a lot of charged particles. All right, so that's why electric fields will penetrate most things. And I've already said this, so those are, this blue thing is the short way to say all of that blah, blah, blah. I say that, it's technically true. Worth noting that factoid there, but I'm not going to test you on this big, long definition. You will get tested plenty by doing this in analytical problems. All right. We're getting close to the end here. Yay. One more example, maybe two, I don't know. We'll see here. There's a whole bunch of stuff at once, so I want to, again, kind of take you through what this is. So Q1, located at the origin. Q2, located at that spot. We want to know the electric field at that location, et cetera, et cetera. Well, let's talk about the location first. So here's the origin. Here's that other location. That means I have a vector pointing in that direction. So again, didn't put it in here because it's hard to draw in this This slide. It's not PowerPoint. It's this thing called LaTeX. It's pronounced LaTeX or LaTeX, but it's spelled latex. So it's a typesetting language, and you use it to write books, journal articles, but they made a special version of it for making slides. And the reason why we do this is in the sciences, we have a lot of equations to write. And the equation editor in Microsoft is okay for some things, but it's generally not that helpful. We need a beefier machine. So I use this tool for that reason and no other. But so we had something located at the origin and something located, like out here somewhere. Okay. And so it ends up being that we're going from source to observation, and we get this kind of a vector going for us. All right. So get rid of that just to clean things up a little bit. And the reason why we're needing this is, remember, ultimately, we need all of the inputs to this equation. I need the magnitude of this vector, and I need its unit vector. Well, in order to have either one of those, I have to get the vector. All right. So one of the things, and so I guess the main purpose of this slide was knowing what you need in advance. If I want the electric field has inputs mathematically. The charge value, which was an easy kill, it's already given. But I wasn't given all of the vector information. I was giving enough information to obtain the vector. Once I obtain the vector, then I can have its magnitude and its unit vector. So hopefully you'll remember, hey, if I have two positions, it's a piece of cake to find out what the vector is that connects those two positions. And once I have that vector, all you're doing to go from this to this is you're taking this input and you're squaring it. And that input and you're squaring it, you're adding them and square rooting them. That's how you get the magnitude. You get the vector by doing simple subtraction. You get the magnitude of that vector by squaring and adding and square rooting, still basic algebra. And then you get the unit vector by dividing those two things. Here's the vector, bam. Here's the magnitude, bam. Divide them, bam. Now we have the unit vector, which is important because here it is. I need the unit vector. I need the magnitude. I'm going to square that number. So I guess the thing to get in your head is there's a bunch of easy math, tedious, but simple math. And once you had those things, then you're just plugging in your check. Then that's an easy kill. So it's a series of easy kills. It's just a lot of easy kills. It's like slow-moving zombies. Okay? If there's not too many of them and you have the right weapon, it's a piece of cake. All right? I'm looking forward to the Walking Dead season next half. All right. Any Walking Dead fans? I'm one. I dig the show. All right. Anywho. And so we go through all this rigmarole, and down at the end here we get a fairly simple output here. Now, the thing that I didn't show, unfortunately, is I forgot to put this here. Okay, that's how we obtain a vector here. So I got to edit this slide. You're thinking, how in the world did you get a vector when all you had in this part here was magnitudes? Okay, so sorry about that. So in the handout, it'll have that put down there. The video is obviously me admitting that I left something out. I was framed. Somebody hacked, the Russians hacked it. No. All right. And then all of that again to get the next vector. Okay, so I'm not going to labor this one. This is all the same stuff. Do all those same things. Get the vector, get its magnitude, get its pointer, so that I can plug in Chugsville. And again, I left out that unit vector. Okay, that goes there. And you get another answer for the electric field at some other location. All right. Not going to labor that because all the math's the same, and you'll get a chance to, you'll have a handout that has this purdy. Now, here's where we're going to do this superposition. So remember in this lecture, we went from here's Coulomb's law, here's how we think about a field. Then we're in this, some examples, and now what is this superposition, this adding up of all the forces? And this time and superposition can be about any vector quantity, forces, speeds, etc. Okay, typically it's forces and fields. So we just went through a bunch of work to get this net field by adding the two things that we had to compute, two identical computations based on data. So here's E1, here's E2, we add them, and here's the net electric field. $2,500 to the right, 6,000 up. The electric field that this thing is going to feel. Now, which leads naturally, some would say. I know people are always wondering this, well, then what's the force on charge Q3? Placed at location A, this location. So we go back to this basic force definition for electric fields. The force at some location is going to be the charge times the net electric field. It's just a reimagining of the field definition, which, if you recall, the electric field was defined to be force per unit charge. All we did was solve it for force. So this value goes in here for E. This value goes in here for Q. You multiply, and voila. Here's the net, or that's the force that a charge of that value placed at the location would feel. Basically a millionth of a Newton in the negative X direction and a tenth of that in the negative Y direction. Again, every step of this is literally advanced arithmetic, but it's busy. It's not your standard XY equations, all right? Now, magnitude and direction of this electric field. All right, how do I do a magnitude? Hopefully you remember, magnitude of any vector means take this thing, square it, take that thing, square it, add them together and square root that, and you will have the magnitude. So our next step is doing exactly that, and we get the magnitude of this field, 6,500 newtons per coulomb. It's the net effect.
if you will, which is a lot. So what's the direction? So magnitude got us to that. Direction, hopefully you recall a little bit of trig, okay? But the tangent would involve the x and the y components. So tangent of theta is essentially a y over x game. And so we could easily make this an electric field in the y and x direction. And that gets us to, if I extract theta, so if I do the inverse tangent of everything, it lets me write theta in that way. So one thing to remember, they'll keep coming up over and over again in this unit. If you want the direction of something and that it wasn't given already, and you know the y and the x components, voila, you are one simple inverse tangent calculation away from knowing that angle. It wouldn't matter what the y or the x quantities were. If you have the y and the x parts, you have the tangent ratio, which means the inverse will give you the angle that it's directed at. So now I know the direction of this. Now, technically, when we had the vector and its xyz components, we had the magnitudes along those component directions. And that would give us the same basic sense that we have here. It's two versions of the same thing. Sometimes this is more useful than the other thing, and sometimes the other thing is more useful than this thing. And in this course, the utility is largely which question you were asked. Outside of that, it's a different thing. And then same thing, what's the magnitude and direction of this force? We're going to do the same thing. Square root of sum of squares. Then I'm going to take those x and y components, and I get the same answer, which I'd better get the same answer for the angle, right? It can't have a different angle, all right? And that sort of proves this. So the main purpose of this slide was this right here. And this has to be true of every vector. Every vector equation, the vector on the left has to equal the magnitude times a pointer. And those things have to be pointing in the same direction all the time. They couldn't be, oh, this one's off in that, and there's a different direction. That wouldn't make any sense. So this makes sense, and all I did in these last two slides was prove that the direction of the electric field and the direction of the force are the same. Right? And I think that is the end of this lecture.